So this is another question for chapter 5. In this question, we have a water that is pumped steadily. So let's highlight that one. So it's just, give me a second. So this is steadily. And then they give us some information about the diameter of the pipe. And it said that both pump here is closed. So we have a pressure at P1 and PV. And then also the energy that pump added to the water, and also we have a head loss. Now the question asking us to find the velocity of the water leaving the pump. So it means that, let's say this is the velocity that's coming out of the pump. Now we need to find the velocity of the pump right here. Now if we have a like system that flow is coming from here to here, right? Let's just name this one as 1 and then this section as 0.2. The assumption that I want to make here is a steady state is incompressible. So we have a steady state flow, incompressible flow, and then also 1D, I mean uniform, and then we have constant properties. Now, one question that I want to ask you, can we use Bernoulli? If yes, why? If no, why? Right? So think about it, pause the video, think about it, and then again start the video. And I think by now you can, if you look at the previous video, you can solve it. So try to solve it and then compare it to the solution that I'm just writing down now. So let's get started and solving this question. So I'm going to use the conservation of energy. The reason that I'm not using the Bernoulli equation is that we have loss and we have work. So it means that we cannot use Bernoulli equation. So now we need to use the conservation of energy, and then if I write it down from point 1 to 2, this is the formula that we have. Right? And now let's see what we have here. So we have P2, we have P1, right? What else we have? What about velocities? So the velocities, if we know that this is a large tank here and a small pipe here, so if we just, the way that we always do, write down the conservation of mass, we can see that both V1 and V2 have the kind of zero velocity. So these are going to be 0. And then let's see what else we have. We have HL. We have HL. And also we have HS, right? Now let's just oh, we don't, do we have HS? Yes, yeah, we have the kilowatt, yeah, the energy. Okay. Now, also we know that the formula for HS is the work into the system divided by m dot over G, right? Which is also, we can write it down as V dot gamma Q, right? And Q is V pump times the area of the pipe, right? And okay, if we, so the reason that I'm writing down this equation here, let me just delete the line that I drew, is that we know that HL and HS, they are in meter in this equation, their units in meter. But the uh, things that we have here is power, right? So we need to kind of change it, change the unit to get HS. So basically we don't have HS, but we can find it. So let me just bring this one down and first simplify this equation that we just wrote down here. So HS is, if we just rearrange it, we have HL plus we have pi 2 minus pi 1 over gamma, and then we have Z2 minus Z1. And then we already know everything here, so we know even Z1, Z2. So if we put all of the values here, we're gonna get HS as 10.4 meter, right? And now we have it here, and if we just and also just one more thing that I wanted to emphasize, the HS here as a positive sign because it's a pump. And it kind of, I also refer to it in the, talk about it in the lecture note, but it's just like for a pump in the control volume, it is positive because it is associated with the shaft work into the CV. This is why, and we said that work into the CV is positive, so this is why it is positive. Now, this question asks us to find the velocity of the water leaving the pump, right? And now let's look at this equation that I write down here, right? We find HS from here, right? And this W dot is the power that's given by the pump in the equation. So we have this one as well. And then let's say we have this, and we have this, right? And then if we look at this one, we don't know Q, right? So we can find Q from here. And from here, when we find Q, I'm not going to write down all of the values, but when we find Q, so we put Q right here, and we know the area of the pipe because we know the diameter, and the diameter, the diameter of the pipe, sorry, the diameter of the pipe is 0.1 meter. So we put the area of the pipe here. We already calculated Q from this equation, so we can find the V of pump. And if we do that, so this Q is going to be 0.0392 meter cubic over second, and this V of pump is going to be V is equal to 4.99 meter per second. Now let's go for the next question. So in this question, we have a large tank and water flows to it and passes through a turbine. And this is the work of the power of the turbine that we have. And then it said that it's just coming out of the turbine, and what we ask to find is, and also this is another important thing, it said that the head loss across the turbine is negligible, but the head loss for the entire system is 2.5 meter. Now they wanted to find the pressure differences across the turbine. So across the turbine, let's see how our flow is moving. So let's say this is the point 1, and then if I just look at the stream, so we wanted the pressure differences across the turbine. So let's call this is point 2 and this is point 3. Now it means that we are trying to find P3 minus P2, right? So this is what we want to find here, P3 minus P2. And yeah, let's just put another number here at the end of the pipe, at the end of the turbine. So first let's write down our assumption. So we can assume that it's a steady state, a steady flow, it's incompressible flow, Bondi and constant properties. So now we are trying to find P3 minus P2. Again, pause the video and ask this question. Can you use Bernoulli equation? If yes, why? If no, why? And then try to solve it and compare your your answer with my answer. So we cannot use Bernoulli equation because we have a turbine here. We have loss through the system. So we cannot use Bernoulli equation. So we need to use conservation of energy. So if I use conservation of energy, I have from point 2 to 3, because we are trying to find P3 minus P2, right? So P3 over omega plus V3 squared over 2G plus Z3, then P2 over gamma, V2 squared over 2G plus Z2 plus HS and minus HL, right? And now let's see what we have. So if we write down also the conservation of mass for this one, we know that n dot 2 is equal to n dot 3, right? And then if I just, oops, how it changed. Oh, I accidentally, I think. Okay, so it's going to be, sorry, just give me a second. So it's going to be row 1, row 2, and A2 and V2 equal to row 3, V3, A3, right? So the same density, they are going to cancel out. So, and the area of the pipe right here and right here is the same. So the area is going to cancel out from both sides. So V2 is equal to V3, right? Then it means that these two also cancel out from both sides. And these are in the same elevation, right? So then these two gonna cancel out also. And then what we have here, it said that the head loss across the turbine is negligible. So meaning that this one is 0. Now if we just rearrange it in a way that we can solve it for P3 minus P2, we're gonna get gamma HS right from here, and then for HS we need to find HS, right? So we know the power of the turbine, so let's instead of HS use the expanded equation of it. So we have W dot S into the system over M dot, and then we have G here, and what else we have? Yeah, that's it. And then from here, if we just again change that M dot with Q thing, so we're gonna get gamma W dot S and N over gamma Q, right? And this gamma cancel out. And from here, we say that in the lecture, if we have a turbine which is in the control volume, the sign is going to be negative because it is associated with the shaft work out of this control volume. So for this W dot here, we are going to put a minus sign, right? And the value is 2500 kilowatt. And because it's kilowatt, you need to convert it to 1 kilowatt is 10 cubic Newton meter per second, right? And then the Q, do we have? Yes, we have the flow rate, which is 20 meter cubic per second, and because the unit is meter cubic per second, it's the volumetric flow rate, right? So this is Q. So we have also Q, which is 20 meter cubic per second. Now from here, we are getting P3 minus P2 is minus 125 times 10 to the 3 Newton meter per squared, or we can also say that P2 minus P3 is 125 kilopascal, right? So either of them is working. Now in part B, we are trying to find this elevation right here, and it said that this is free surface here, so we have a P atmosphere right here. And also another thing that we can say about section 1 is that we have a large tank, right? By the conservation of mass that we always did in the previous chapters, so we can say that V1 is approximately 0, right? So now we are trying to find H, and for that let's use point 1 and point 4. So again, so this is part B. We are trying to find H, right? And now we are trying to, now let's just write down the conservation of energy between 1 and 4. So now what we have, so P1 is to the atmosphere, so this is 0. P4 again is to the atmosphere, this is 0. So V1 we say that's a large tank, this is 0. So if we consider this one as our datum, this is going to be 0, and then Z1 is going to be H, right? If you look at the picture, right, this is H, the difference between Z1 and Z2 and Z4. Now, what else we have? So we are trying to find HL, right? So we know HS, right? Because of here, because we have the W dot, so easily we can find this one. We don't know HL, but how about V4? Let me see if we have V4. We don't have V4, but we have the area here, right, which is the same as the area at 4, and also we have the flow rate here, so we can easily find it. So let's first find V4. So V4, we can just relate it to Q and A. So we know that Q is VA, so Q4 is V4A4. Then it means that we have this one, we have this one. If you put all of the values, you're going to get V4 as 6.37 meter per second, right? And then we can put V4 in this equation and then solve it for HL. So Z1, which is H, is equal to HL, right? And then minus HS and plus V4 squared over 2G, right? And then from here we have 2.5 meter plus 12.8 meter plus 2.1 meter, and then this is the value we are getting for H. Now let's solve this question. In this question we have a horizontal pipe, and there are two sections, which is like a T section here, and the water flows as from here and here as a free jet. Now the information that we have is the velocity at this point. Let's call some point here. If this is 1, which the flow is coming in, and this is 2, which flow is going out of 2 and 3, we have the velocity of 2 and velocity of 3 that both is equal to 15 meter per second. And then what we have, it said that assume there is no, the frictional losses are negligible. Now what we are trying to find is the resultant force, right? So resultant force. So the first equation that comes to our mind is conservation of momentum. For conservation of momentum, we need to follow this step. The first step was to draw a control volume. So now I consider my control volume. This is the time to consider my coordinate system, right? And now this is the time for showing the velocities, which is inflow and outflow to the system. So this is V1, right, which is inflow. This is V2, which is outflow, and this is V3, which is outflow, right? So let me just delete all of the V here. And then what else we need to consider? So pause the video, think about it, then answer me. So the next thing is we need to consider all of the forces to the system, right? Because we are trying to find the resultant force. So let's again just assume we have the resultant force like this, and this is the Fy, right? We have weight for sure. What else we have? So we have three opening, meaning I have three forces at the opening due to the pressure at the forces. So I have P1 here, and we are going to multiply it by A1 to get the forces. So this is P2 times A2, and this is P3 times A3, right? Now the assumptions is like before. I'm not going to write it down again, but then also I think there is one missing. Yes, but okay, we are going to talk about it. So let's now we are going um, to apply both conservation of mass and conservation of momentum. We always start with conservation of mass because we know that we are going to need it in conservation of energy. So if I write down conservation of mass, I know that there is one flow is going in, and then, for example, if this is like a small control volume, we have one is going in, is coming out from here, and then coming out from here. So this one right here should be equal to the adding of these two together. So it means that the mass flow rate going to the system is going out to the sum of the mass flow rate out of the system, right? So it is equal to V1 A1 V2 A2 plus V3 A3, right? We know what do we know? We know A1, we don't know V1. We know A2, we know A3, we know V3, and we know V2. So we can solve it for V1, and then V1 is going to be 12 meter per second, right? And now let's just apply the conservation of momentum, linear momentum, and we know that this is the formula for the linear momentum, right? We know that this is mass flow rate, this is velocity. The sign of velocity depends on the direction based on the coordinate system that we assign, and then the m dot, it depends on inflow and outflow of the flow. So conservation of momentum, let's just write down it in x direction, and let's look at the system. In x direction I have fx, which is positive, then I have p1 a1, which is also positive. I have a minus p2 a2 because it's in the negative direction, and then I don't have any other forces in x direction, so let's go to the right hand side of the equation. So we have v1, which the sign is positive because it's in the positive x direction. I have m dot here, it's inflow, so it's going to be negative. Then I have v2, right? It's in the positive x direction, it's positive, and then I have m dot 2, which is positive because it's outflow, right? Let's see what I have and what I don't. So P1A1, I don't have it, right? And then P2A2, it said that it's related to the atmosphere right here. So this is going to be P of atmosphere, and because of the P gauge, it's 0. So what else I have? I have V1. Then it means that I know m dot 1 because I know the area. I have V2 and I have m dot 2, right? So what do I then? I don't have Fx and I don't have P1. So I have one equation, two unknowns, and I already using my um, mass equation, the conservation of mass. So it means that I need another equation. So let's also write down the linear momentum for y direction. So for y direction, if we look at uh, the pipe, we have Fy, which we consider to be positive in y direction. Then we have a weight, which is negative. What else I have? I have P3A3, which is also positive. P3A3. Then for the right hand side, V1 and V2 is in x direction, so I don't need to consider it here. But I have V3, which is in the negative direction of y, so we have a minus sign for it. And then I have m dot 3, and m dot 3 is going to be positive because it's outflow. Now let's see what I have here. So what I have here is I also have a weight. So let me just write it down, weight here. This is given by the question. So let me just write it down here. The overall weight means the water and pipe is going to be equal to 100 kilonewton, right? Now we know that we have weight, we don't know Fy, P3A3. So P3 is also is into the atmosphere, so this is going to be 0 again. I have V3, I know m dot 3. So two equation, three unknowns. So I cannot solve it too, but I can find Fy from here if I solve it. And then if I solve it, I'm going to get Fy is going to be 3 to 56.7 Newton, right? And now let's see what other equation that we can use. So I'm asking you one question, and then pause the video and try to think about it. Can we use Bernoulli equation? Why not? Or if yes, why? If not, why? And or can we use the conservation of energy? Think about it. So we know that the conservation of energy is kind of the Bernoulli equation. Sorry, the Bernoulli equation is our conservation of energy, which is reduced to the Bernoulli equation because of the neglect in losses and because if there is no work. So here, if we look at the system, we don't, it said that assume there is no losses. I mean, because of the neglect, they said that assume that frictional losses are negligible. So this is why we don't have any losses. And if we look at the system, we can see that there is no work. There's no turbine, no pump, or no other work. So it means that we don't have any works there, right? So it means that we can use the conservation of energy, sorry, the Bernoulli equation. We also can use conservation of energy, but when we say that HL is zero and HS is zero, it basically means that we are using Bernoulli equation, right? So let's just write down we are using Bernoulli equation. And we are using Bernoulli equation. Let's see, we are trying to find P1, right? So because we are trying to find P1, let's just use from 1 to 2, because for example, if I want to use from 1 to 3, I don't have any information of this distance, right? So it's better I'm going to use uh, the streamline between 1 and 2. So we are going to use from 1 and 2, and let's write down the Bernoulli equation. So this is the Bernoulli equation, right? So let's look at the values that we can find. So Z1 and Z2, they are in the same elevation, right? So it means that they are going to be the same, so they are going to cross out. So P2 is pre-atmosphere again, this is 0, and then we have V1, we don't know P1, we know V2, and yes, we can find P1. So we have 1 and 2 equation, and we have 2 unknowns. We have P1 to find and then Fx to find, right? So let's solve it. Now if we solve it, we are going to find P1 is equal to 40,000 for 60 Newton per meter squared, or we can just simply say that 40.5 kilopascal, right? And then if we just put this, if we call this equation number 1, and then substitute this value to equation number 1, so we can easily solve it for fx, and this is what we get for fx, right? And also it's negative, and we know that it means that the assumption that we made is wrong, right? And yes, that's it, I think, for this question. And we can also, oh, it wanted us to find the resultant force, not the anchoring force. So let's solve it for the resultant force. So we know that the resultant force is equal to B minus of our F CV, which means that the forces on the CV, the anchoring forces, right? And this resultant force is the forces on the fluid. Forces on the fluid. And if we just, let me see this, okay, we have Fy here and we have Fx here. And if we want to find R, which is the resultant force, again we need to just kind of add them, not add them, just using that, for example, if we want to find the magnitude of, for example, let's say velocity, and we have ax plus bx, then the magnitude of velocity is going to be a2 plus b2, right? So the same thing we can, sorry, so the same thing we can do for the forces because it's vector, right? So if we look at, we say that we have a minus sign for fx, meaning that fx is going this way, and this is the fy, because the assumption that we made for if fx was like this, but when we get the minus sign, it means that our assumption was not correct. So this is the way that we can just see it, and then this is going to be f of cv, right? And then now the rx, we say that it's negative of FCB, right? Then it means that Rx is going to be, let's just round it by 72 kilonewton and round this one by 32.6 kilonewton, right? I have a minus sign here, sorry, I forgot. So then Rx, we have a minus sign, right? So minus sign times Fx, so minus Fx, this is going to be 72 kilonewton, and then Ry is going to be minus Fy, so this is going to be minus 32.6 kilonewton. And the way that I calculated for theta in the previous questions, and also the value of R, right? The magnitude of R, you can do that and find it. So the magnitude of R is going to be 78.96 kilonewton, and then theta is going to be minus 24.4 degree. So the way that I'm talking about is like, let me just show you. Uh, yeah, right here. This is how, just use this one. So this is how we calculate the theta and the magnitude of our forces. So these are the questions that I solved for the conservation of energy, and try to practice them by yourself and don't look at my answer till you uh, solve it by yourself.